Okay, good morning. Today we will start our first seminar on the basics of nuclear chemistry, and today we will see how simple math problems are solved within these courses. We will start with type of decay, and first I will explain some simple equations, some simple basics, what we will do today. First of all, I would like to remind you that the energy of the nuclear decay, we can calculate the value of this energy from the defect of mass. So it is quite simple equation. We know it from culture, I don't know, from everything. That energy is equal to mass multiplied by the velocity of light squared. And when we talk about the nuclear decay, that means that we have some radionuclide, the parental radionuclide, let's call it X, with the charge of the nucleus Z, and we remember that the charge of the nucleus is equal to number of protons and the mass of this radionuclide M. And we have some sort of decay. At the moment it not very important what type of decay it is. And let's say that we have another charge of the nucleus as far as we have another nuclide. That means the charge is different. And mass, it can be different and can be not, but let's assume it's another one. And it can be particles like beta particles, alpha particles. Let's call them just some letter, let's say B. It will be any particles. And to calculate the energy that is produced during the nuclear decay, let's call it Q, like heat that is produced during the chemical reactions. It is this defect in mass multiplied by velocity of light squared. What is the delta M here? Delta M here is the difference in masses between the initial radionuclide and the sum of masses of the produced particles. So we can write it like this. It is mass X minus sum of M, let's say Y, C squared. And Mx here, it's the mass of initial radionuclide, and the sum of My, it's the sum of masses of the products. From this equation, E equal to mc squared, we can recalculate the masses to energy. So as far as we are talking about nuclear decay, and decay is related to a single nucleus or to a single atom, it is more convenient, more useful to speak about the masses of single atoms and the energy that is released during decay of the single atoms. And if we will use the conventional units of masses like kilos or grams and units of energy like joules, we will obtain very tiny numbers like 10 to minus 27 kilos and etc. So it's not very convenient. And for us, it will be more useful, more convenient to use masses of single atoms expressed in atomic mass units. Okay. And we can calculate what the energy will be related to the mass of one atomic mass unit. And it will be equal to 931,501 kilo electron volts keV, or if we express it in mega electron volts, it will be like this. Okay. And another useful unit that we will use many times, it is mass of one electron. That is also expressed in energy units. It will be equal to 511 kilo electron volts. Yeah. Okay, and as far as the mass of protons and neutrons, they're more or less the same. Mass of neutrons a bit higher than the mass of protons, but there we can say it's around one atomic mass unit. And from comparison of these two numbers, we can say that the mass of protons and mass of neutrons approximately 1,840 times more than mass of electrons. And again, mass of neutron a bit more than mass of protons in reality. So we can see that the electron is very tiny particles, very light particles, and in many equations that we will use later, we can neglect it, but not in all cases. We will see it from our experience. So now it is about the energetics of nuclear decay. And now we will talk a bit about different types of decays. So I need to clean this board. Now about the different types of decay. We will talk about alpha decay, beta decay, and gamma. And so what is the alpha decay? If we have our initial radionuclide X with Z, M, and we produce radionuclide Y, and the alpha particle is emitted, and the alpha particle, it's actually the nucleus of helium with the charge 2, as far as it is helium, and with mass 4. That's why the charge of the daughter radionuclide is decreased by 2, and the mass is decreased by 4. Because in total, if we summarize these charges and masses, we should obtain the same as it was before. So it is the alpha particle. Beta decay. Actually, it is 3 types of decay. It is beta minus decay, beta plus, and the electron capture. And beta minus means that if we have, let's say, again, the radionuclide X, Z, M, we produce radionuclide Y, and the beta minus particle. and the beta minus particle actually just an electron. But when we write these equations, it's better to use beta minus expression, because with this we distinguish between the electrons that are located on the orbital shells of the atom and the electron that are released from the nucleus. So it has a charge -1 and the mass around 0. So we can write for the charge of the daughter radionuclide or just nuclide that it is increased by 1, because here it's -1 and in sum it should be again just Z. And the mass of this nuclide, daughter nuclide, should be just M, because the mass of electron is very small and we can neglect it in this equation. But it's not only two particles that are produced during the beta minus decay. There is also the very tiny particle that is called antineutrino, and in this case it is anti-particle. That is for beta minus decay, and now for beta plus. So let's take again our favorite radionuclide X, and if it is beta plus particle, so it's simply the positron. So that means it is the antiparticle to electron. It is the same mass, the same spin numbers, but the charge is +1. So we can write here +1, mass is still 0. That means that the charge of this daughter nuclide will be -1 in comparison with the parental radionuclide, and the mass will be the same. And there is another particle, and in this case it's called just neutrino. So you can see if we produce just an electron, we produced anti-particle, anti-neutrino, and if it is anti-electron, positron, that means that the third particle will be normal particle, just neutrino, not anti-neutrino. And the electron capture, the same radionuclide, and the electron capture actually means that the electron from electronic shell, from orbital shells of the atom, is captured by the nucleus. So it should be plus electron from the electronic shell, and we produced another nuclide with neutrino. And how we should calculate the charge of this daughter nuclide? So again, we have to sum the charges of the parental nuclide, radionuclide, and the charge of the electron, and it will give us the charge of the daughter radionuclide. And the mass is the same, as far as the mass of electron is very small. So what is the neutrino? Neutrino is a very tiny particle. It is a particle from the it is lepton particle also, as electrons. Leptons, they have three types of particles. It is electrons, neutrinos, and muons, and they have antiparticles. For electrons, it is positron. For neutrinos and muons, it's antineutrinos, antimuons. And the charge of the neutrino is 0, so it's neutral particle. And the mass is also almost 0. We still don't know the exact mass of neutrino. We only know for a moment that it is at least 200,000 times less than mass of electron. And we remember that mass of electrons around 2000 times less than mass of protons. So that means that neutrino has a mass around 200 or 400 millions times less than mass of protons and neutrons. So it's very small, very light particles that is difficult to be detected. And we still don't know the exact mass of this very small particle. So, and the gamma decay, actually, it is just a transition from the excited state of the nucleus to the ground state, or to a lower energy state of the radionuclide. And gamma quantum, it's just an electromagnetic wave, like a visible light, just with the very high energy. So, from all these equations, what we can say as chemists? First of all, in all cases of alpha and beta decays, we have a transformation of nucleus. There is a change and in number of protons at least. That means that we change our element. And for alpha particle, as far as the charge of the resulting nuclide is less than charge of the initial nuclide by 2, that means that we should move in periodic table by 2 cells. Let's say it's just cells in periodic table, for example, I don't know, let's take it radon. Here is polonium, here is astatine. And if it is alpha particle, then it should be francium. So it's the first period, it is the 8th period, 7, 6. So if it is alpha decay, then we should move by 2, and we will we will stop at polonium. If it is beta minus, that means that we increase the charge of the resulting nuclide. That means we should go to the right by 1 cell. And if we have beta plus, the charge is changing by 1. It decreases by 1. It means we can go by 1 cell to the left again. And the same is for electron capture. It is the same Z minus 1. It means we should go to the left by 1 cell. And it is not only how we can write it and show it. There is also a schematic representation of the decay types. And we can simply draw it like this. For alpha decay, it is double arrow or thick arrow going down to the left, because we are moving to the left in periodic table. For beta minus, so it's alpha, it's beta minus, we should go to the right, and it is a single thin line. For beta plus, it is also thin line, but directed to the left. It is beta plus. And for electronic capture, it is dashed line, electron capture, also directed to the left. And for gamma decay or gamma transition, as far as there is no change in charge or in mass, So it is the same element, the same nuclide. Thus, the line is directed straightly downwards. So it's just a gamma transition. So this is how we can represent different types of decays, and in many tables, in many data book, you can see these schemes, and now you can read these schemes, and you can more or less understand what is going on. And now we will look on just few examples. Let's solve this task. So we should understand what are the hidden radionuclides and what are the resulting nuclides. So thorium 229 has a charge 19, so it is an element 19 in periodic table, so Z 90. So how can we solve this task? So we should remember that during the beta minus resulted in Z plus 1. Alpha decay resulted in Z minus 2. Beta plus resulted in Z minus 1. And electron capture is the same, it is Z minus 1. So small reminder for us. And now we are looking on the, let's start with the radionuclide C. That is the beta minus decay. So that means that the charge of the nuclide was increased by 1. So previously it was another nuclide with the charge 89. And thus we can write, so where is it? Yeah, that C, it is something with the charge 89, and the mass is the same as it is for thorium, so it is 229. Okay, and we can go to the periodic table and see what is the element corresponding to 89. And if I remember correctly, it is the what it is, actinium 89. So then we should go back to radionuclide B. It is also beta minus decay. That means that the charge was increased by 1, and thus the parental radionuclide has a lower charge of the nucleus with the charge 88. And the mass, as far as it is beta minus, mass doesn't change. The mass, it is just a small reminder again that the mass changed only in the case of alpha decay, by 4. Thus we can write that it is 229. And again, we should go to periodic table and see that it is radium. And radionuclide A. Again, beta minus 87. Mass is the same. It should be a francium. Okay, so we now understand that ABC, it is francium, radium, and actinium. So what about the D? I will write it here. So for D, it was electron capture. That means that the charge was decreased by 1. Thus, the D means that it was something with the charge of the nucleus 91. Mass, again, doesn't change. That is 229. And again, we should go to periodic table of elements to see what is the element number 91, and it is protactinium. Yeah, and now we are going to element E, or radionuclide E. Again, electron capture, mass doesn't change, so it's probably uranium. So now we know it is D and E. And now we should understand what is F, G, and H. So, and H. We know that it is alpha decay, so we should decrease the charge by 2 and the mass by 4. And we already know that number 90 corresponds to thorium, so it's thorium. So for protactinium, again, it is alpha decay, and we can easily calculate the charge of the nucleus, like 89, and the same mass, 225. And again, we already know it's actinium. And now for thorium, it's alpha decay, thus the charge is 80A, mass again 225, and it is radium. So it is just an easy task, but from doing this, we can easily understand how the chemical composition of the material is changing during different types of decay. Also, if we know the resulting radionuclide, like in this case thorium 229, and we know the type of the decay, we can understand what was the parental radionuclide which decay resulted in our nuclide that we observe. Okay, so now we will go to the next task. How many alpha decays was during this transformation from thorium 232 to lead 208? How we calculate it? Also, we will add additional question, and how many beta decays were there. So, how to calculate this? In principle, you can, many people are starting from the charges 90 and 82 because it looks like it much more easy to calculate the difference in charge and to guess how many alpha decays it was. So you can calculate that the difference in charge is 8, and you can assume that it was only 4 alpha decays. But it is wrong, because if we will calculate the difference in mass, it will be 16. Thus, the mass of the resulting radionuclide should be 232 minus 16, 16. But we have 208, the mass. Thus, the mass, the difference in mass is 208 is equal to 24. And again, we know that the mass is changing only during the alpha decay. There is no changes in mass for beta minus, beta plus, or electronic capture decay. Thus, if we see the difference in mass, it can be related only to alpha decay. Thus, from the difference in mass, we can calculate how many alpha decays it was. So it was 6 alpha decays. We can write it 6 alpha. And now let's calculate how many beta minus decay were there. Again, we know what should be the changes in charge due to the 6 alpha decays. It should be 12. Yeah, it should be Z minus 12. But we see that the actual difference in charge is only 8. So, minus 8, yeah? Minus 8. That means that this difference in the observed difference of charge and the calculated difference in charge due to alpha decays can be corrected by assuming the beta minus decays. And how many beta minus decays we should take? 12 and minus 8. That means that it should be 4 beta minus decays. In this case, we will add 4 beta decays, and we will get our observed difference in charge like this. So, from these simple equations, even if we don't know the whole chain of the radioactive decay, we can easily say that it should be at least 6 alpha decays and 4 beta minus decays. Of course, as far as we don't have the full picture, the full chain of radioactive decay from thorium to the lead, we cannot say for sure that there were no other decays. For example, it can be additional beta plus and additional beta minus decay. There will be then no changes in charge and no changes in mass, but these additional decays can be in the whole chain. So it was the first task, the second task, and now the third task. So we should calculate the maximum energy of the particles released during the decay. And to do this, we can simply estimate for beta decay. It is only for beta decay, any type, beta minus or beta plus, it doesn't matter, that the maximum energy of the released beta particles is equal to the energy of the nuclear decay. And the energy of the nuclear decay, we remember it is delta mc squared. or we can simply calculate it using this mass coefficient, where delta m is expressed in atomic mass unit, and then this energy will be in mega electron volts. So it's quite an easy task, but it is correct only when we don't have additional gamma quantum. Why? Because if we have gamma quanta that are released as a consequences of the beta decay, that means that the part of the energy is going to the gamma quanta. And if we know the energy of the released gamma quanta, we should take it out from the energy of the decay to calculate the maximum energy of beta particles. But this is not the case for this task, so it is rather simple. So we know the difference in mass for this task, so it is just this number. And we can, in this task, we can simply multiply this number by this difference in mass. So I will take 9.8 mega electron volts. So it is quite a big energy. In general, the energy of the decay, the radioactive decay, is has a very high energy related to the strength of chemical bonds. Again, I will remind you that the energy of chemical bonds or chemical reactions or whatever is only, let's say, few electron, 5 to, I don't know, 100, let's say, electron volts. It is for chemical bonds for very heavy elements like uranium, thorium, and others. The energy of electron bonding in atom can be very high, go to few kilo electrons volt, like 17 to 19 kilo electron volts. It's very high energy of electron. It is K electron. So it's electron located on the K shell of the atom. But for chemical bonds, so it is energy of the interaction between the electrons on the outer shells of the atoms. So their interactions not so strong as interaction between the electron on the inner shells of the atom and nucleus. And this energy is just tens, let's say, of electron volts. And the energy of the decay is started from tens of kilo electron volts to mega electron volts. So you can see easily that the energy of nuclear interactions is 1,000 times more stronger than energy of any chemical bonds. So it's very nice example. And now we will go to the next task. So we will calculate the energy of the alpha particles. It is a bit more difficult task, but only a bit. So for alpha particles, what is the difference when we talk about the energy of alpha particles and beta particles. So it should be not n particle, it should be alpha particle, but nevertheless. Okay, we have this simple transformation of radon to polonium and alpha particle. And now, so I think I can, make it like this. What is the difference with beta particles? In case of beta particles, we could neglect the energy that goes to the recoil nucleus, because beta particles and neutrino, they are very tiny particles, and they got almost all the energy that is produced during nuclear decay. And it is not the case for alpha particle. Imagine that we have our initial nucleus, our favorite X radionuclide, and we have a decay. In the case of alpha decay, we see that we produce only 2 particles. And there is a law of conservation of impulse, of movement, that says us that if we have in the beginning the pulse equal to 0, so we assume that our initial atom was resting, so there was no moving, 0 velocity. That means that the sum of the pulses for produced particles should be also 0. And it is a vector. That means that M1 V1 should be like minus M2 V2. So it is 1 particle, and this is a second particle. That means that they goes to the different directions with the angle 180 degrees. And from this equation, we can say that the scalar multiplications should be equal to each other. Also, and for M1 V1, M2 V2, we can simply write that it is mass of recoil nucleus and velocity of recoil nucleus, and the mass of alpha particle and the velocity of the alpha particle. And we understand that the energy that is produced during the decay goes between the alpha particle and recoil nucleus, if there is no gamma quanta released again. So from this we can calculate just the kinetic energy of this particle. So it is m alpha v alpha squared divided by 2 plus m v squared divided by 2. So we know this. We know this ratio. From this, we can take, for example, the velocity for recoil nucleus. It will be a ratio between the masses of recoil and nucleus and alpha particle. Sorry, here it should be alpha particle, velocity of alpha particle. And we can take this expression and take it for this equation. So what we will get? So it will be the beginning the same, plus m alpha squared multiplied by velocity of alpha particles squared divided by 2. And from this we can extract just m alpha v alpha squared divided by 2. And here it will be the sum of 1 plus m alpha divided by m recoil. And this expression m alpha v alpha squared divided by 2 is just the energy of the alpha particle. Thus, we can rewrite it like this. Equal to energy of alpha particle, and here it will be this ratio, m recoil, m alpha divided by m recoil. And from this we can recalculate the energy of alpha particles as the energy of the decay multiplied by this ratio. From this equation we clearly can see that the energy of alpha particles will be always less than the energy of the nuclear decay, because this ratio will be always less than 1. The question where the rest of the energy goes, because we have the whole energy of the nuclear decay, Q, and the energy goes not only to alpha particles, but also goes to the recoil nucleus. And the energy of the recoil nucleus will be almost the same expression. The only difference will be that instead of mass of recoil nucleus, it will be the mass of alpha particle. So we will need these two expressions to solve our task. Let's go back to our task. What we have from the conditions of this task? We have the masses for radon, for polonium, and for helium. Thus, we can calculate the difference in mass. So it will be mass of radon. Mass of radon minus mass of polonium and mass of alpha particle, or helium-4. Thus, it will be very long expression, because this number is quite long. 222 017 7379 minus mass of polonium 00896 897 and minus mass of helium-4, 4002603 and it will give us, I don't need the very long numbers, so I will put it like this. So, and it is atomic mass units, okay? Yeah, okay. And now we should calculate the energy of the alpha decay. So the Q will be equal to 1 multiplied by 0.006. And again, I will reduce the numbers to this. It is mega electron volts, 5.59 mega electron volts. But we should remember that it is not the energy of the alpha particle, because the energy of alpha particle that we just wrote, it is the Q multiplied by the mass of recoil nucleus, and in our case it is mass of polonium divided by mass of recoil nucleus, means polonium, and the mass of alpha particle. Thus we should multiply our number 559 by simply 218 divided by 218 plus 4. In this case, we don't need all these small numbers because they will not give us any big difference in our calculations. Thus, we will got the number 5.49. Again, it is mega electron volts. So we obtain this number, and we see that the difference in the total energy of the nuclear decay, 5.59 mega electron volts, and the energy of alpha particles is around 0.1 mega electron volts, and this energy is not lost. This energy, it is the energy of the recoil nucleus, and in our case it is the polonium 218. So we calculated not only the energy of the alpha particle that is released during the nuclear decay, but also the energy of the recoil nucleus. And again, it is important to remember that the energy of the recoil nucleus in the case of alpha particles is very high. So it is 0.1 mega electron volts. It's 100 of kilo electron volts. And again, we should remember that the energy of chemical bonds is just few electron volts. Thus, the energy of the recoil nucleus 1,000 times more than energy of chemical bonds. And thus, if we had, for example, some chemical or some molecule that contains the alpha-emitting radionuclide, that means that the recoil nucleus will definitely go out from this molecule, because there is no such a chemical bonds that can withstand such a huge energy of moving of the recoil nucleus.